Welcome to the stream if you're watching in the future. Let's see, I have to set up some stuff here to get the chat working as intended. Let's see, yeah, this one got set up correctly. Custom browser, blah blah blah. Let's change this. And let's set it up to be live chat. All right. I do think things should be set up correctly. Okay, so during the last stream, I guess I was a bit tired after doing all the matrix inverse stuff here. I mean, just look at it. It's well, almost 200 lines of code. Um, I'll definitely look into the optimized version. Also, I'd probably implement a optimized 3x3 inversion um, function. Hello, buddy. Um, yeah, I'll look into that in the future. I'm no math genius. I know how to use the math and how it works, but the explicit details of it is not my strong suit. Anyway, I did a bit of debugging last night and I realized there was a bug inside the inverse matrix calculation, which resulted in some odd behavior. Then I also made sure that we had the correct camera. And then I realized that we're using a right-hand sided coordinate system. Therefore, I had to flip the C direction since forward, quote unquote, is actually along the negative C axis in our coordinate system. So yeah, we fixed that. And I'll show you all the results of our stuff here. Let's enter a mode where we can debug. And yeah, also I added object highlighting, as you can see here, which I think is pretty neat because whenever we implement collision detection, we would like for some whoops, as you can see, I immediately started casting rays. I didn't realize. Anyway, since I was clicking up here, it seems like the rays are cast the right way. Anyway, let's just redo that. Anyway, so if I click here, okay, I should enable the debugging information. Let's redo that. So if I click here, well, the ray is cast straight forward. If I click up here, the ray is cast upwards. If I click down here, the ray is cast in the correct direction. So let's try rotating the camera here a bit. Well, it even works if we rotate. Okay, one last thing I need to test is whether this works on any camera or if our camera controller gives us trouble. So yeah, it seems like it works on every camera. Let's try the free floating one. Yeah, it seems like it. Okay. As the debug mode lets us know, everything is surrounded by bounding volumes represented by the green outlined boxes here. And that's a sphere approximation. It's of course not a true sphere, but each point is guaranteed to be inside the sphere. I think it's called an icosahedron. Anyway, so we would like to do some collision detection between the rays here and our bounding volumes to let us know if we actually hit an object. And then we want to couple that with our what do you call it, editor. So um, my day is pretty good. How about you? I've just been at work doing different stuff. Yeah, how did your test go? Oh, that's great. Well, even though you wanted to ace it, it's probably still quite alright. Hello, buddy. How are you doing? Uh, so we do actually have an implementation here. But I would like a probably faster implementation. So let's do a I'm doing quite alright. I've just been at work all day and yeah, got home, decided to do some streaming. I just showed Mr. Yes here that I fixed the problem from yesterday. Let's just, right now I'm not casting rays, so now you can't see anything. But yeah, let's enter debug mode here. As you can see now, our rays are getting cast in the correct direction from the camera, no matter what kind of camera I use. And also I implemented some highlighting on the objects that are selected. How come your day was crazy, Mr. Yes? Thank you. I definitely need to change the texture for the highlighting of whatever active object we have. Just plain white doesn't look that great. Um, I'm thinking something like maybe a what do you call it? Yeah, maybe some kind of like construction orange, or if you know what I mean, construction sign orange. Oh, that sounds rough, man. Why why was it beyond torture? Let's do SAT, Ray, AABBs, check. Let's do segment because oh, that sounds rough, man. Those old school curriculums where someone insists on doing something very dusty are never that great, I reckon. Okay, how could we speed up this? Let's do a vector. Yeah, you're pretty far for an 8th grader, I'd say. It's pretty impressive how much you're able to do with information technology, I'd say. I wish I were at your stage in grade 8th. Let's see, ray origin, ray direction. We will simply copy the parameters here. Yeah. FDT, are you in your 20s, 30s, or 40s? Or beyond? Because I'm more than halfway towards my 40s. Oh, so many young people in the chat. How nice. Makes me not feel as old. It makes me feel rejuvenated. But also envious of all of you who decided to do this maybe even decades before I did. So this is a way to get the actual intersection points and distances. I reckon at least the points. We don't care about this because it's just a test, a fast separating axis test. between a line segment and a series of bounding volumes. And let's see how much we can optimize this. So we need the box center, which we have stored in our bounding volumes here. So let's just do an auto. Let's just be verbose here. I'm ambivalent in terms of doing the auto keyword in C++. We should also actually make them constant. I try to remember every time, even though I haven't done it here. I'll redo some stuff eventually because making all of this constant makes the compiler here const. There we go. Go. Vroom, vroom. I'm sorry if I butchered that meme. Anyway, so we will use our sender. Separating axis theorem is concerned about finding separating axes between shapes. You project these shapes until on their uh, um, face normal axis. You could say for each face on a polygon, there's a normal, and that normal represents a potential axis which separates two polygons or two faces. So yeah. I felt a bit too old to use that meme. I'm I'm pretty sure it's only allowed for people in their mid-20s and below to use that part of the internet culture. But I decided to take a chance anyway. So we will project the ray here onto our um, our box. So the origin of the projection will be our box, and if the origin translated into box space, let's see, our origin in box space overlaps with the projection of the box in that local space. We have an intersection. If not, we do not. So let's see. So we have the origin. Let's just say that is our now. When we cast the ray, the origin is at our camera. So if we scale it up along the ray direction, actually we could hard code here const float distance, which we will set to something like 100. We'll create an endpoint. We will create an endpoint here, a gvector endpoint, where we simply ask our math library here to add scaled vec. So we will add our origin together with our direction, and we will scale the direction by the distance here. We have a nice intrinsic based function to handle that, so that will be pretty fast. As you can see here, it's pretty simple. Not very many instructions, or rather, not instructions, cycles. And we can well, our midpoint would then be our, let's see, we want a midpoint, we want a half-length vector. What's the fastest way to get the half-length vector? Is it just well, the midpoint will be half the distance here. And we can do, so our midpoint here, and then we can actually do a the half-length vector would be the endpoint minus the midpoint. Yeah. We could just type something out here. Let's see. Yeah, let's do some quick stuff and then think about it later. Half length. Vector vector subtract vector subtract. Yeah, there we go. Okay, and if we pass in the endpoint here, vector scale, vector scalar, add scalar, multiply scalar. Here, our midpoint. No. Maybe we want a scale vector 3 again. Add scale vector 3. So midpoint plus array direction, distance times the last half here. That will be our endpoint, and then we will subtract our midpoint. All right, let's set the midpoint here. Oh, that will be on a per box basis. So let's do a projection midpoint equals our midpoint math vector subtract our midpoint here minus our volume center. Not yet, not yet, but it'll be something of the like. We do have components of sorts, but there's no generalized system that handles them. Also, I'll be probably changing the underlying structure into something that is more struct of arrays friendly. So it will be consisting of micro components and component archetypes that are cache friendly aligned structures that can be submitted for speedy computations. So I mean, it depends on your definition of ECS of sorts. Let's see. Let's see. Okay, so we have a projected midpoint where we simply translate, not projected, translated, where we take the array midpoint here and translate it alongside our, what do you call it? So that the box origin, or rather center, is the origin. So we basically move that midpoint. Then we want to check for separating axes. Let's see. So separating axis theorem. Let's as you can see here, we do a projection. If the two endpoints here for each polygon overlap, we have no separating line between them. If you could also say if the radius of each object calculated from their centers doesn't overlap, we have a separating axis. Yeah, I'm not sure I explained it very good, but Uh, yeah, true. That is true. Um, only convex objects. So we can get the absolute uh, value for the length of the um, race um, segment. We computate a segment here with a midpoint and a half length here from our array and our direction, and given a certain distance of the segment. Um, anyway, we can get the absolute value of the we can actually pre-computate these. We don't need to do them for each box. Let's do an absolute check here. Do we need to specify the type here? No, it doesn't care. It will through operator overloading. We'll do fine. Yeah, since we're doing several computations here, comparisons here, uh, we will pre-compute these beforehand. If you were only comparing to one AABB, you do, of course, these intertwine, meaning that first you check if the x-axis is a separating axis, and then you exit the function. If it is, then if it's separating on the x-axis, you proceed to the, or rather, if it's overlapping on the x-axis, you proceed to the y-axis and then do the check and exit out, and yeah, so forth. But since we're doing multiple comparisons, we try to pre-compile whatever values we have beforehand and not do them every time we do a singular comparison. The translated midpoint needs to be unique for each box and its specific center. So let's do uh, uh, yeah, we would actually like a vector here of unsigned int of collisions. Let's just reserve a bit of space here. Bounding boxes size divided by 4 or something like that. I can't imagine that we would collide with a lot of bounding volumes. Anyway, if the also absolute is actually a also a computation that we would do. Let's see, apps midpoint x. Yeah, we could play around with doing these. Well, maybe if we have an early out, we yeah, I guess it depends on the actual case itself, which is faster. But we want to take the midpoint here of the x-axis and compare that to the box volume here. Let's rename that to box. box dot half width on the x-axis plus the absolute value the absolute value for the x-axis. Yeah. If this is the case, we continue. Whoops. Let's see. There we go. So let's try to draw whatever we actually just did here. Can I? Okay. Paint is sort of. There we go. So we are projecting. Let's see. Let's see. Can I see? We have an axis. We have a separating point. Let's just whoops, maybe like this, and then let's do a box with no fill, and let's say we have a yeah, I'm not sure how to draw it when we're doing a line here. Ray segment. But it's basically something like this. If the midpoint here and the half length of this, we're basically translating as far as I see it. We have a line here. Let's imagine we have a line with a midpoint here that gets translated. Whoops. Translated by the origin here. So we translate it into object box space. So if this part, this half-length vector, length, or what do you call it, component on the x-axis, plus the half width, half width here of the box. If these two distances plus each other are lower than the midpoint, we can't be intersecting. Meanwhile, if we have a box where we have the length of the half width of the box and the line segment. It must be overlapping on this axis, if you know what I mean, because the distance between this center here, which is translated into box space, and the length on this axis here, which would be actually represented by this line here, plus, oh, whoops, plus of course the box half width. If this is lower or equal to these two lengths combined, the ray segment would be overlapping the actual box. Hello, it will be a shooting game, I think, with a bit of physics. Have you ever played? Yeah, I will probably do something Doom-ish, but I also remember that I played this game as a kid and really liked it. Um, so even though we won't do any what do you know, IP related stuff. I think we will have some fun with the physics engine and try to implement some gameplay elements that uses that. So imagine something like a hybrid between um, Doom and maybe Dark Forces. So maybe something like a telepathic Doom guy or whatever. Yeah, at least that's my idea. It might not turn out as interesting as I hope, but well, yeah, we'll see. All right, let's compare the midpoint y here to the half width of the box on the y axis and the y um, length of the ray segment, and let's do the same thing for the c here. Okay, so this tests whether there um, uh, is an separating axis. No, I'm not sure. Is it something machine learning related? I haven't actually looked much into the CUDA programming stuff, but I'm guessing it's using some kind of asynchronous compute only pipeline. Maybe someone else in chat knows something about the topic. And usually in separating axis theorem, you also do a series of cross products. Does it need to be physics based? Well, yeah, that's pretty simple. I suggest that you look into FTC. Okay, yeah, that's a really great question. I don't know if well, if you have some way of accessing memory directly by address, I mean, DirectX is able to specify virtual addresses in GPU memory by giving you a uint 64 with the actual address. Well, I guess if you are allowed to work directly with those memory addresses, and you can do specific lookups on certain memory addresses in the OpenGL API, I think you would be able to do some interoperability. But I don't know the exact workings of the underlying API and if you're allowed to do that. I suspect that you could do something of the like between Vulkan and DirectX since it's so close to the hardware anyway, and probably works with local memory addresses in virtual memory. So, but I'm not certain, but uh, it would make sense that you would have so much control over the hardware that those APIs can kind of like communicate together. Uh, those pieces of API, I mean, types of API. Anyway, um, Rengoku, I suggest that you look up Ian Millington physics engine. Um, he has a really great book uh, on on doing physics game engine programming in C++. He has a pretty easy particle system implemented. Um, and it will be even easier to implement in 2D. Um, so, but in general, you would do something like um, object integration. It uses C++. But generally, a particle system is something like no problem, man. I'm happy to help the way I can, or if I can. But Rengoku, let me show you quickly. I will not use a lot of time on it, but um, I'll give you a generalized outline here on a particle system here. So generally, a particle system relies on you integrating between frames. Integrating means updating and applying forces to particles um, for each frame relative to your frame timer, which is usually your time step, delta time, call it whatever. Um, and you integrate each frame using Verlet integration, for instance. That's a type of integration. Let me just type it out in the chat. or Euler integration, I think. Let's see, Euler integration, yeah, physics, explicit Euler integration, and you can use um, the second version of that. Um, yeah, um, use that for integration of your particles. Particles are really simple objects that are easy to calculate. Oh, okay. Yeah, you could use that instead. There are different advantages, and yeah, it de and then after you integrate, you check for collisions, and you do some logic depending on if your particles collide. Do you want collision resolution? Because then you would um, um, add something like do collision resolution for all the particles that collided. And for instance, that would handle if objects are supposed to bounce off each other or get destroyed when they collide or whatever. Um, yeah, that's some great advice. Um, And then you want to couple this physics system to your rendering algorithm. So you might update your circles or quads or whatever primitive you're using for your particles directly from the physics properties, for instance, related to their position in screen space or whatever. Um, you could also create different planes, meaning that maybe the screen has bounding areas where the particles bounce off when they collide with that, or whatever. But that's the basic step. You integrate, you check for collisions, you correct the collisions. You could do something like destroy objects. You could, of course, do that. Before you check for collisions, if they have a lifetime of sorts. Um, you could also do some subsystems like particles that collided spawn new subparticles or whatever. You could do different steps, but in general, you want to integrate, check for collisions, and do collision resolution. And you simply just set so that on click your application spawns maybe one particle per. Yeah, I think second order Euler is pretty fine, even though there are probably way better and more stable algorithms. Let's see here. Inside this. This is a Euler-based integration step. So you simply update the position, calculate the total acceleration. You could use force accumulators of different kinds and apply forces inside the integration step, and then you calculate the velocity and you dampen the velocity. Yeah, for particles, it's pretty simple. And suppose you have a screen where you want the particles to drop down on the screen, you simply apply gravity to all particles, and then they will overlap eventually. And you use collision detection in a grid-based pattern where you simply partition your screen into maybe grids of different sizes. You iterate over each square and check for collisions inside that square. You could do that multi-threaded, and then you do collision resolution on the collisions themselves. Yeah. So that's the basic step. The basic steps. That's plural. And you can play around with different integration steps, doing them before or after collision detection and resolution and whatever. There are so many variations and trade-offs that you probably, yeah, but yeah, that's true. But if you just want to create particles that get spawned from the mouse and maybe drop down, drizzle down towards the bottom position of the screen, I'm thinking constraints are probably a bit overkill. I just do simple sphere colliders for every object, and since they are so easy to test, I mean, sphere collision detections are so fast. Um, and then if he has a lot of objects, he should do screen space partitioning. In general, the guy who developed the Box 2D, which has been um, um, a very big inspiration point for the physics bullet engine and almost every physics library that have seen use in modern gaming. Um, his way of handling constraints is something of an iterative approach. I don't think he does linear solving. It's linear solving seems like um, more related to commercial physics engines for like testing of cars or whatever, as they're simply too slow for games. But I've been considering doing a linear approach, testing out how complicated a system you could do with sufficient multi-threading. It would definitely be interesting. Yeah, 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 yeah. There's a whole field of different stuff to explore, and I mean, um, I'm by no means a physics nor programming expert, but yeah, I feel like particle systems, maybe using simple constraints if you really need them, but only if you really need them, are a great place to start. Not yet, at least. I don't think the code base is, well, um, something that I want to share for now. Maybe if I end up actually succeeding in building this game, I could imagine releasing the source code. Um, since I'd probably use the prototype to do another iteration on the another iteration on the engine for my own use in a different project. So yeah, maybe I'll do that, but it's way out in the future, and it's only if people really want to access the source code for some reason. Um, if the game uh, against all odds should work out and be something that people actually want to play, I think um, yeah, yeah, most of it is documented here on the live stream, but I've done work offline, especially during the development of the physics stuff that hasn't been documented because I spent almost 3 weeks, uh, 3 weeks on tracking down a quaternion math bug. Uh, yeah, I spammed the forums at gamedev.net because I simply couldn't figure out why my objects weren't getting oriented correctly and had such weird behaviors. Turns out it's really important that your math is working properly. Who would have known? Anyway, it was an interesting discussion. It seems like there are some really knowledgeable people here on the stream. It's really nice to have resources like that. But I should try implementing the rest of this algorithm here, because the thing is, as I've mentioned, the separating axis is actually the since we're doing testing of the line segment against an AABB, is the world space coordinate system axis. We need to do a check whether um, the cross product. Let me just think straight here. So let's see. The cross product between the segment direction vector and the face normals, which are basically the same directions as the actual coordinate system itself. So we will test these cross products, but because a line may be parallel to the specific axis we're testing against, the cross product between the line segment, and that particular axis would be 0. So therefore we add a small epsilon to all of these absolute values here. So that we never try to compare a close to 0 value to a close to 0 value, and thereby wouldn't be able to discriminate whether one value is bigger than the other. So let's see. Let's do the absolute. We could also pre-compute the second part on this. The midpoint y component times the half length c component minus the midpoint c component times the half length let's see, the half length y component here. And we could actually pre-compute this because wait a minute. Oh, I've made a mistake here. I can pre-compute this, but I can't pre-compute this because it's actually the translated midpoint here, of course. Yeah. The translated midpoint. Okay. Anyway, we compute that. And compare it to our box half width y component. This is the radius on the apps e. Let's see now the CE here, because that's the one with the epsilon plus the half box half width C component times the apps YE. Of course, we need the registers here. Okay, let's see. So the Y, the C, the C, the Y here. Okay. And let's copy this, but change it, of course. So now we take the C component, the X component here, the X component, the C component here. So this is the y-axis. And then we have the X and the C, of course. Then the C here. then the x. Is that correct? Wow, I'm not sure. Let's see. Okay, thanks for dropping by and thanks for the sub, man. Good luck on your project. Yeah, I can always compare this to my other separating axis test. Okay. Let's see. We do the x, the y, y, x. No, I think it's correct. And then it should be lower than the x, y, y, and the x. Otherwise, we have a collision. Okay. In I, put 0I lower than bounding boxes dot size. Then we need the index here. I and collisions pushback I. And that should be it. Okay, let's take this for a spin, as they say. So let's include our collision checking stuff here. We have our array. We can, it's a T. Did I? Oh, it's inside the general collisions. General. Did I namespace it? No, it should be. Oh, it's actually general collisions. There we go. Array origin, ray direction, and then let's give it our static bounding boxes, and let's just do a distance of 50 because I think that is what we're using here. Yeah, so we can actually visually see our arrays, because I think they are slightly short enough that we don't end up in a situation where we actually by default intersect with the objects. So let's see. Okay, if we of course need to output our collisions here. We need a std vector reference of unsigned ints. Out collisions. Let's see. There we go. And we of course need to add that to our method here. Okay, we should actually add that before the standardized parameter. So let's just swap these. There we go. And let's do the vector here, vector collisions. Pass that in. Okay. If the collision size, then for, let's just do the auto here, auto val collisions, collision with index and then the val here. And let's just do a new line, just in between frames. Okay, let's see. Cast ray, and as we can see, our ray doesn't intersect, but we intersected with object number 3. Let's see, if we just click on object number 3, we cast another ray, but now we collided, that ray collided with object number 1, which is that one, and it seems like it's working. So object number 2, well, object number 0, well. Okay, so great stuff. Let's see if we can use our free floating camera here to set up a situation where we collide with multiple objects. Let's see. Let me just see. Oh, it wasn't long enough. Yeah, we collide with multiple objects here, 2 and 3. Let's 2 and 3, yeah. So our algorithm works. Pretty great stuff. It traverses the objects in order in terms of their creation. So we could do some comparisons between, for instance, the distance between our ray origin, which is our camera position, and the maybe center of our object, picking the one that is closer to us. That's not a brilliant way to do it. We could also just implement the collision detection algorithm that decides to give us a distance to the actual collision point that uses yeah, I think it's the distance at least. Yeah. Or is it the intersection depth it gets us? Let me see. Let me see. It's a basic yeah, it is the intersection distance. So we could simply parse that out instead. That would be a way of uh, yeah, we could do that. It depends on what we would like to do. Mm. It depends on what we like to do. Mm. We should also rename this, I think. Intersect. Whoops. I accidentally copied the wrong name here. Okay. We could implement the other algorithm. Yeah, let's create the other method where we get the actual points. Hello, how you doing? We could do a ray intersect AABBs. Did we already do that actually? Actually, maybe we did. Yeah, we actually do this. Already? So there's no need to redo that. I mean, let's see. So if we use this, let's create a version that takes maybe same but different parameter. A GC vector, a const here. We don't want to store the I don't think we want to store the actual. Yeah, let's see. Okay, we will start by implementing it with the output here, and let's decide on what to do. We will be doing that. Bounding boxes. This is a const here. And let's see, a const. This should be right because, yeah. And then we do not have a problem anymore. Okay, we collect a series of points. We could also create a series of distances. Let's just, let's see, pushback. Let's see, let's add the distance here. Okay, so instead, yeah. The more I work with C++, the more I really prefer C. I should do a entire game engine in C someday. Okay. Let's see, unsigned in. Oh, it's the index here, actually. Actually, this just. Let's try passing out the float here, out distances. Let's do that for now. Let's see. Am I editing the correct one? No, I'm not, am I? Ray intersects, there we go. Let's see, correct one. Okay, so now we get all of our information out from this check here. General collisions, ray origin here, ray direction, and the static bounding boxes, and then we give it our collision indices here. Let's do std vector flow distances, and then a std vector of g vectors points. Print an index. Of course, we need to for loop this. Auto reference. Call in collisions. Call dot. Whoops. We need the int I stuff here. I less than this. Often I think that I can get away with just using the 4-element iteration, but I usually find myself wanting an indexed version. No, it doesn't make sense. Try referencing a com pointer, for instance. On top of that, there's some weird abstraction where you get a different type suddenly instead of a memory address. I mean, some parts of the C++ standard library is so convoluted and hard to read, and the compile times get so massive whenever you do meta programming like templates. So yeah, it's definitely not elegant. I do think that C++ has its applications. Um, but I mean, there is some bloat, I'd say. No. Yeah. Generally, I don't like the standard library, but yeah, I've gotten accustomed to the C++ way of doing things, so I guess I've just learned to live with it, and yeah. Distance. Okay, let's do some whoops, testing here where we do multiple collisions. So uh, so index 2 has a distance of 28 and index 3 has a distance of 33. Let's see. Oh, whoops. So 2 is this one and 33 is this one. Let's see if it checks out for every instance of the test. So index 4 has the distance of 26, so it's closer. Okay, so it's actually the closest distance in terms of the origin here. Let's just check it out. Item 1, yeah, okay. So if we want to be able to grab the closest object, which we do, we should use this one. Let's see. Let's create a version that all the same but different parameters. I mean, operator overloading, or rather overloading, is also a messy part of the C++ way of doing things. I think it's neat though. Sometimes it does make your life easier, but it may end up resulting in things that are harder to dissect or read or whatever we call it. So we want the indices and the distances. We could also just do the logic. We could rename this to something like get the closest AABB. Get ray, get closest intersect ABB. We could do something like that. And then remove this and simply compare the distance. Float, previous distance. Float max here. Closest distance, let's do that because it's more obvious what we actually do. Unsigned int. Now let's do an int here. Index equals 0, we will return an int here, return index. We don't want our collisions or distances or anything. We just want the closest object index. And we will copy this. It will be a different method, of course, because we're doing something else. This is the SAT version and basically the same SAT version of the above for fast intersection checking. Okay, so this should give us well, if it doesn't intersect, we don't care. Then if the distance is smaller than the closest distance, we update the closest distance to the distance. And then we set the index to I. Actually, yeah, we didn't need to do that. For some reason, I hit the wrong button and end up in a situation where I write it like that, but okay. And this should give us the index of whatever is the closest. Would we like a version that doesn't pass out a point? This could be pre-compiled, pre-computed for efficiency. Could be moved outside of function since it's the same for several boxes. And let's do this. Yeah, we could do the last. Okay. Well, let's see. Could do a version that doesn't pass back the point since we don't use it. Okay. And now we can simply change all this and closest AABB equals the general collisions ray origin, ray direction, static bounding boxes ABBs. And we could simply check if this closest AABB index is higher than or equal to, or just higher than -1. We could set our object here. Let's see. Yeah, so I think I have this update here automatically. Now, that's neat. Let's see. And as you can see here, I can now click on whatever object, and our object list here also updates. I effectively now have object picking. Great stuff, great stuff. Then, of course, we should look into, whoops, let's not print that to the console. Okay, we actually still cast the raise. Yeah, I want to disable that. Otherwise, as you might see, we end up with some really messy screen stuff here. Let's keep that function for now. Should not be kept, but useful for debugging with raise outside the application. Anyway, it is working. Let's try moving around our camera here. We can simply click on our objects just to select them, and our editor index gets updated appropriately. This only supports static objects, so I can click on Paul or the player, but we could easily implement that. Paul is an OBB, OBB oriented bounding box. So we would simply do a intersection test with a distance like that. I think it's probably a version of the SAT for the OBBs, OBBs, since they are, well, they are modifiable to do that. Otherwise, we will look into different algorithms. Whoops. Yeah, but it's basically more of the same. We now cast the array correctly, and we translate all the way down to world space. We could do local object space and simply do some uh, collision detection there. If you wanted to be able to select specific um, triangles of each mesh, you would have to do a overall bounding volume check like this, and then you would probably translate into local object space, and then for each triangle in the mesh, you would check if the ray itself um, intersected with the according or that triangle, and then it would store which triangle was closest probably to the origin here of the array, and you would know which triangle got selected. But yeah, we're not doing manipulation of each triangle in each mesh inside of this application here. So we're perfectly fine by creating bounding volumes that we usually do for our static meshes anyway, since we are planning that they are meshes that are collidable inside an overall environment. So we don't want to waste CPU cycles translating into object space coordinates, and even though world space coordinates might be prone to rounding errors due to floating point precision issues, yeah, I still don't think that we need a specific and very precise picking algorithm that can handle that situation. Maybe if you had very, very large maps, you would prefer to translate into local space of the bounding volume. But yeah, I don't think the scope of this project is that big. So anyway, we have a working picking system. Let's check our overall plan here. We did some math. We did object picking. Let's not remove it because we still want kind of check, but need it for OBBs and spheres plus all types of objects. Also, this could do scene bounding volume chunking to speed up ray collision detection, meaning that instead of going through every object in our scene, we could simply cast a ray through our scene, which would be divided into chunks of 3D bounding volumes, and we would check a series of chunks according to how far we cast the ray, and of course how many objects there are inside each chunk. So if the closest chunk doesn't have any items, we move on to the next chunk. And then if it doesn't have any items, of course, the next. And then if it has several items, do a more precise collision detection test inside that volume to see whatever object is the closest. But we do not have a overall chunking system of our world space just yet. That will follow with our physics engine when it gets further developed. Okay, but I think that was great. Um, so one last thing I want to add to this system here is we select an object, and as you can see, the highlight texture here changes with the change of the object. I do a simple comparison. If the current object is different from the last frame selected object, we revert the object back to its original texture. But when we exit the editor mode, nothing resets, as you can see here. So that is not great. I'm unsure whether we could force a situation where we simply do something like, well, if we're in the update step, since I flipped the textures here, as you can see, if the editor last frame object index is unequal to the editor object, and we actually have some static objects to check between, we grab the currently selected object and set it to a temporary texture using our update function with only the texture flag. And then if we actually had selected an object last frame, we reset that back. And then we update the value. So whenever this changes, we make sure that each time it changes, that we deselect. So I'm wondering, maybe we should just, if we're in the we could invalidate it, but I'm not sure. Uh, we could do one last check here. If this is equal, or rather the editor index is equal to the maximum number of a uint, well, then we wouldn't do this stuff because we would invalidate our current selection. But what happens if we swap back to the back to the back to the editor mode, then we would have a very high index and we would get problems with our vectors being not big enough. So maybe the easiest way to do this is to set up some sort of cleanup flag. Bool editor cleanup, and we will set that to false. Maybe. And if we've ever done this, we need an editor cleanup. Uh, and we could do something like should we do this every frame? Do we need to do it? I don't think so. Let's just check if everything still works. Okay, so if we need to do a cleanup, if editor cleanup, we will basically do this. Whoops. This was actually a bug. Okay. And then we, of course, set this back to false because we have done it. Okay, let's see. Okay, right now. Oh, wait a minute. It will be automatically true. Each frame. Let's do the application state check as well. Okay, so only when we're in that state we clean up. Well. And we, of course, want to do it to our currently selected object. Let's see. Well, that doesn't work for some reason. Does it even end up in this state here? Ended up in state. No, it doesn't. So let's check. Do we not? Default 9. Am I not pressing the... Well, let's just check the console here. Default. Well, we should be in default mode. Okay, let's just check if we're in default mode. Or if it doesn't agree that we're... Oh. I know what's wrong. I'm inside the wrong scope here. I'm actually inside the editor mode, checking if we're inside or in the default mode. Yeah, that doesn't make a lot of sense. Okay, there we go. Okay. Yeah, the first time I start the editor mode, it simply ends up in that state. Maybe I want to because right now but this might crash because of vector subscript problems. No, okay. So it doesn't check unless we actually click on anything. Yeah, okay. That works way better. Right, Paul? Bug. Okay. I think that was pretty neat. Pretty neat. So what should we do? Okay, we already did this in the application here, so that can be deleted. We're still at a point where we want to do more work on the functionality of the editor. As I've mentioned in the previous stream, I need to do some more UI work in order to be able to do this in a somewhat elegant manner. So what I'll do off stream, probably during the week, because I'm pretty sure I might not have the time to do any streaming before the weekend. But what we will do is clean up of some of the UI, and we will definitely add a bordered 1 pixel text. I'm about to, I think, because yeah, I need to do some different stuff and do some cooking and yeah, maybe go to the gym and yeah, I have to go to work tomorrow and I have a pretty busy day at work. So yeah, I gotta get prepared for that. Thank you, man. I think everything turned out pretty well. Um, we implemented the object picking from A to Z over the last 2 episodes here, and we made our application a bit more nice. created some UI interaction, and yeah, I think this level editor is gonna turn out quite all right. Yeah, I think this is pretty nice. Okay, I should stop playing around with it. Uh, it's actually not a game yet. um, so we want the UI to have bordered text. I mean, for instance, the white text here should have a black thin border that makes it more readable. We want better scaled text so that we can write small text fields, small font. Oh man, that has been a long project. Um, yeah, it's being rendered directly by DirectX. I have a coupling to my own renderer directly. So it's both text and primitives, basically squares that get drawn to the screen. We clear the depth buffer and then we render the UI. You could even do blending so that it blends together with whatever scenery and it's semi-transparent, and yeah. Um, Let me show you real quick. So inside the renderer here, um, I have a series of draw calls. Our render call here begins the frame and does whatever it needs to do with polygons. Then we have some, what is this? This is going to be removed and implemented inside this part where we do some debugging, drawing, and this is more debugging. And then we draw an UI, which is basically these what do you call it? I call them render data structures, not debug primitives, UI elements. And this is basically a data structure that um, both describes rectangles and glyphs, as they're called, but we could also call them letters and numbers. But each glyph is a UI element where it has a screen position in normalized device coordinates. So it's the X and Y here because the screen is only 2D, and then a width and a height. And then we map onto a texture atlas with specific texture coordinates. So yeah, the text is actually described by vertices. Each letter or number is a set of 4 vertices. A quad can be drawn from 6 vertices, but if you do indexing or triangle lists, as they're called, you can actually get away with only describing 4 vertices for a quad. So, yeah, imagine that we have a series of glyphs here, A, B, C, D, E, F, and then this UI element here describes where on the screen to draw it with and how big it is supposed to be on the screen with the first series of numbers here. These 4 numbers describe the position and the height and width. And then this texture coordinate system describes, well, where in the underlying texture atlas am I supposed to map to? So for instance, if these values have certain numbers I might map onto the texture like this, and then this will be cut out and stretched out on whatever surface I described here, and the areas where there's no text are transparent. So where the underlying glyph here is not transparent, I apply this color. If it's transparent, of course, I don't do anything. I just discard the pixel. So um, basically, like imagine that this is like it's just an image. Imagine that all the black areas are transparent. So this quad here has 4 vertices. So one here, one here, one here, and one here. So if I kind of like cut this texture here by a series of 4 vertices, which each their own coordinate inside this texture, and I use each 4 corners as yeah, exactly. Everything in the UI are basically blocks, like squares, and the only difference between a letter and a rectangle or a quad or whatever is actually the underlying texture. So of course for rectangles, I can show you inside the renderer here. For the I do UI elements, which are basically just quads primitives, and I bind a specific texture, unless you know DirectX terminology. Um, well, do I do that? Yeah, I do. I manipulate the currently set texture array inside the shader to a base white texture. That simply means that every pixel on the rendered quad is drawn. No, that would be highly inefficient. It's way easier just to texture map and render a bazillion quads. Have you ever seen those old games where, for some reason, there's probably a memory overflow or something on the GPU, where every character is just a square box, or not a square box, a rectangular box. The renderer breaks down, and every glyph of UI is just squares. Uh, I don't know if you remember games that could crash like that, or where the renderer could break down like that, but back in the day I remember that, and that's actually what's happening. You render these quads that have textures which just happen to be text. Also, I remember if you tried to play a game with a graphics card with too little memory, you could end up in that situation. Yeah. Yeah. It's basically because the renderer doesn't know what to render to the screen, so it just maybe renders a box with the base or standard texture. Yeah. So each character is kind of like a series of 4 vertices each, but never more than 4. And you do something like called instance drawing, so it's pretty fast. It's like uh, um, batching. So they are kind of like drawn all at once. Not really, but close to. At least it's highly what do you call it? Optimized. In DirectX 11, batching was way harder, but no problem, man. Um, and then the overall logic of creating the UI is actually handled on the CPU. So it's basic computations on. Yeah, I took very much inspiration from the ARM GUI. Um, at first, I did my own way of doing an UI completely from scratch, and it ended up being a convoluted mess that had no scalability. So I looked at the DRM GUI API and got some hints on what to do. So everything that needs to be scrollable or open closable or draggable or whatever functionality you want is a window which is a defined rectangle somewhere, and you can create sub windows or child windows on each window, which means that they themselves can have elements or scroll bars or whatever. For instance, let me see. I don't know if I've shown it. Yeah, this actually automatically creates a scroll bar here because it's like a sub window, and yeah, the way that immediate mode UIs are made um, is that they are calculated each frame. So uh, for each frame, the CPU kind of like does a series of work in terms of figuring out which UI elements should be sent off to the renderer. Of course, you try to steer around any memory allocations. You don't want memory allocations to happen very often since they're very slow. So you try to allocate as much as you can, and then reuse whatever allocations you have for each frame, so that the CPU work is basically updating data fields and doing some small calculations on how to adjust sizes or how much you're scrolling or whatever. Um, yeah, it's been fun, but it's been a lot of work, and I haven't implemented a fixed delta time yet, which is also the reason of a bug here. Um, Let me show you the bug in just a second. I've considered it. I don't know if we need the fidelity of a fixed delta time. If we were doing something like a fighting game that has requirements for frame specific precision, I mean, you should be able to, in a fighting game, to time your actions approximately to different keyframes of animations in order to block at the right time or whatever. Uh, in that case, I would definitely do a fixed delta time, but since I'm doing a shooter, well, I don't think I need to, but yeah, we could do it. But let me show you the bug here. So when I drag the window around here, the messaging system kind of pauses the application. So when I release it, Paul goes through the floor, through the floor because the delta time gets massive, and the physics system doesn't handle such massive increases in delta time, since delta time is always lagging behind by one frame, so to speak. So it's like the distance between previous frame and this frame. So yeah, it's not as linear as you would probably like. Yeah, if the physics stability is a high priority, uh, I think fixed delta time is the way to go. Or you could do two systems: a overall delta time the uh, um, for the actual rendering, and then you could do simulations on a tick basis. I think games like Factorio, for instance, have both an FPS and an UPS. They are closely linked, but generally um, uh, it relates to how many update cycles do I do per second, in contrast to the actual rendering part. And if you want fluid simulations, you of course want the exact update per second, but you could care maybe less about the frame rate. So you could do multiple systems. And yeah, of course, you're welcome to message me. All right. I think that was it for today. I feel like it's been a really nice stream. We've had a lot of different folks drop by, interact, and participate in fun discussions. Also, just a quick disclaimer, I'm by no means an expert or professional. I might have an opinion, but that doesn't mean I'm always right. There are probably so many nuances that I don't even know, so yeah, keep an open mind. Uh, nah, yeah, I have to call it a day. I've been at work, and then I've done the stream, and then I'm gonna do some stuff, and then it's probably gonna be bedtime for me. I didn't get much sleep last night. I think my mind was uh, contemplating the whole inverse matrix thingy. Yeah. FTC, which area of the world do you live in? Which continent? Okay, it's fine. It's fine. All right, guys. Thanks for having hanging out. It's been a total pleasure. I look forward. Sorry about that. My headset sometimes shuts off for no reason. It works properly the most of the time, but then it decides to shut off. Anyway, it's been a pleasure, and I hope to see you around. If anyone is watching this in the future, If you found it helpful, inspirational, entertaining, feel free to comment, like, or subscribe. I hope to see you around. You are very, very welcome to join the live streams. Next stream will probably be during the weekend, except for if I end up in a situation with a lot of time on my hands. All right. Take care, everyone. Be kind to yourselves and keep on trucking.